Thank you. Thank you for all the organizers for organizing the conference. And thank you, Doug. One of the things I wanted to say was it's amazing. Every time I start looking at a problem and you sort of look for, what's been done, Doug's name is always there. And it's not just, a little side note. It's a central piece of, oh, this is how you will solve the problem eventually. And he just sort of leaves it for somebody else to do. So thank you, Doug. So I'm going to talk about things that are very similar to Andrea's. It's a similar problem, similar notation. So I'm going to zoom through the notation because you just saw it. I'm going to talk about the Oberwolfach problem. She talked about the Hamilton-Waterloo problem. We're very similar problems, very different methods that I'm going to talk about. It's a seeding problem, as Andrea mentioned, and here's Doug waiting for a seat. We have MI, a set of tables, each of size MI, at the venue. Hang on, where's the, there, whoa, okay. Well, here's an example. The one thing I'll just mention here is the notation here. OP M1, M2, MT means there's tables of size M1 up to MT. Okay, here's an example. We've got the round tables here, one of size 3, one of size 4, and another of size 4, 2 of size 4. Here's our first seating. Here's our second, third, fourth, and fifth. So in 5 nights, everybody has sat next to each other. And of course, you're all noticing what a wonderful solution. Look at this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. This has got a nice cyclic property. And one of the things that I'm sort of interested in here are these nice, in this case, one rotational type of solutions. And I'm very happy that Marco's here because I'm going to be quoting him a lot. Okay. You've seen all of the, you've seen all of this before. 2-factor is a spanning two regular subgraph. The big difference, of course, is that I put my what's going on? I put my exponents on the right. Andrea put hers on the left. Okay. Other than that, it's all the same. 2-factorization. We're going to decompose the edges of the complete graph into this 2-factor that we've talked about. We can generalize to arbitrary 2-factors. I'm not going to do that. I'm just going to talk about a single factor, and that's the classic Oberwolfach problem. Okay. So this problem asks for an F factorization of the complete graph KV. Now, if you think about it very quickly, you'll realize each factor is going to use every 2 edges from a point. So the number of points is going to have to be odd. The number of edges incident at a point is even. We'd like to be able to deal with the case where V is even. So the sort of classic way of dealing with that is we remove a 1-factor, right? So we talk about KV, and we just remove a 1-factor. And now all the edges have even degree and everything's good. R, the number of factors we're looking for, will be V minus 2 over 2. But there's also another way we could go, which has not received as much attention, but there's no real reason why not. And that is, instead of subtracting a 1-factor, we add one. Okay, so I'm going to denote these 2 problems by OP minus if we take away a 1-factor, and OP plus if we add a 1-factor. Okay, minus, take away, plus, add. And then we have this general notation where we talk about OP sigma. Sigma is 0, 1, or minus 1, depending whether we don't do anything with 1-factors, we add 1 or subtract 1, though not in that order. Okay, so this really goes back to the original work of Kirkman, who famously introduced the problem with the 15 schoolgirl problem, which also sort of famously was not solved until the 1970s by Rayshard-Hurry and Wilson. Probably the most useful classical thing for us is the Valeshky construction, because a lot of what we're going to do is kind of reminiscent of Valeshky. It's known there's no solution in these 4 cases given here. However, every other instance, it is with v less than 60 is known to exist. Okay, and that was originally up to 40 was done by various people there, and then more recently, Tommaso and Marco and various other people extended that to 60 in a very nice way. The uniform case is solved, and of course there's Doug. And you know, Andrea said we used this paper for the odd case. She didn't mean for the odd case. She meant for the case where V is odd, and it does contain a lot of the machinery that you really need. It's a very good paper. Okay, Tommaso did the case where 2 tables, and of course with even cycles, bipartite graphs. Hagfist did I never remember which way around it is, 2 mod 4, and then we did 0 mod 4. We extended that about 10 years ago. Of course, there are also asymptotic results known for the Oberwolfach problem. Dukes and Ling give constructive Wilson-type constructions. Going back to 2007 in the uniform case. And Wilson type means they have Wilson type bounds. They've got stacks of exponents on them. And of course, more recently, it's received a lot of attention. Glockjuice, Kim, Kuhn, and Ostis have shown asymptotic existence using probabilistic methods. So the pros of this is it shows eventual existence. Hey, so that's good. The cons are that bounds are very hard to find. They can't really say, you can't say, well, everything greater than this V0, it exists. You just know eventually it exists. The other problem is that it's not constructive. You can't actually hold one in your hand or make one. And the third problem is there's no structure or symmetry. In fact, because the methods are random, almost the opposite. So I'm looking for all 3 of these things, right? I want some nice symmetry. I want some constructive method that will actually give the object to me. And I want a bound on how big things have to be for this to all work. Just before I go on, this OP plus problem, as I said, has received much less attention. There has been a bit of work, 3 to the T, going back to some work of Doug again, in '87, and then more recently, not that much more recently, Esther and Mills. And then more recently, we have this uniform case with a possible exception. And then from the sort of bipartite case, the standard Hagfist doubling type construction gives you some sort of existence results in that case. Okay, so I talked about symmetry. I want symmetry. What does that mean? Well, we're going to talk about pyramidal factorizations, F pyramidal factorization. So what that means is it's an automorphism of the design of the factorization that fixes exactly F points. So the sort of classic ones are when F is 0, that's cyclic, or well, regular cyclic if it's the cyclic group. And the minus, if F is 1, it's 1 rotational, so 1 fixed point. And this example here shows you a fixed point solution. Okay. We can also, of course, talk about 2 pyramidal, and we'll talk about that in a minute. But let's just look at this nice 1 pyramidal or 1 rotational solution here. So we got 2 4-factors and a 3-factor, a cycle, I should say. And there it factors K, whatever it is, 9, 10. Okay. All right, so we're going to use this idea of 2 starters. So that's exactly what that was. It's a 2-starter. And the idea is that the difference is I take some set of cycles which exactly cover the points, and contain every difference in Z2n. I'm assuming that my group is even, exactly once. And if I rotate it halfway, I get the starter I started with. Okay, so that's the F plus N is F part. And of course, this is essentially Velitzky. This is exactly how Velitzky works. You take this sort of Hamilton decomposition, rotate it halfway, and you get back the decomposition you started with. So, okay. The reason these two starters are really nice, or one of the reasons, is that if you have one, then there's a one rotational solution. Well, there it is. That's where we started from. But there's also a two pyramidal solution. So what I do is I just add an extra infinity between the 2 points that were going through infinity to begin with, and that gives me my two pyramidal solution. It's going to fix infinity and what I've called infinity 2. Maybe infinity prime would have been a better name. And there's a cyclic solution. I just get rid of the infinities altogether, and it all kind of works out. So that's really nice. From one thing, I get a one rotational, two pyramidal, and cyclic solution. Okay. So the next ingredient that I need is graceful labelings. So in a graceful labeling, what I do is I take a labeling of the vertices, and it has the property that if I look at the difference between any pair of vertices on an edge, all the differences appear exactly once, up to plus and minus. Okay, so here's an example of a graceful labeling of a cycle of length 7 and an edge, a single edge. And these graphs are actually the kinds of graphs that I want to talk about. So if you look at the title, Oberwolfach problem for single flip two factors by graceful labeling, just told you what a Oberwolfach problem is, told you what a graceful labeling is. Here is a single flip. So the idea is that we're going to take an involutory automorphism which reflects exactly one cycle. So in this example here, that's the cycle that's being that's being reflected. And if you think about it, there's sort of two possibilities other than that one. You could sort of have pairs of cycles that appear, right? Sort of this cycle gets mapped to some other cycle of the same size, obviously. Or you could have an even cycle where the edges kind of get mixed up somehow, but you still end up with an even cycle. And remember, what we're doing here is every the edges are flipped, right? So there are pairs of edges that get flipped. Okay, so what that means is that if V is odd, so there's going to be an odd cycle in there somewhere, at least one. One of them is going to look like that, right? And then maybe some more odd cycles that look like this, and then some even cycles that look like the one on the far end there. And if you just look at this notation, so we got this one that's odd, 2L0 minus 1 plus 1, whatever. Then we got a bunch of things that are even. So these twos represent those ones that are even. And then we've got these which appear in pairs. They may be odd or even size, we don't know, but they appear in pairs. So L squared. Okay. So possibly one odd cycle, bunch of pairs of cycles, and a bunch of even length cycles. And then if V is even, well, we just don't have the odd length cycle. But same idea, we got a bunch of even cycles and a bunch of paired cycles. Okay, so that's the sort of single flip notion. Now, one particular class of single flip graphs that we're very interested in are what we call zillion graphs. And I realized that actually, well, never mind. The reason why we call them zillion graphs is because you've got a, okay, so what are they? First of all, you've got a path and then a bunch of cycles. Okay, that's all it is. One path and a bunch of cycles. They're sort of interesting because they have the sort of tree property, n points, n minus 1 edges. They're not a tree, of course, because they're not connected. Whoops. Okay. Right. So they're called zillion graphs because that looks like a 1, and these all look like zeros. Right. And here's the notation here. There it is. So we got a bunch of cycles and then a path. Really, the path should have come first, right? Because that's the 1. Anyway. So Tommaso, a while back, proved that if you've got one path and one cycle, you can gracefully label these things. And a lot of what we're sort of going to end up trying to do is gracefully label these types of graphs. Okay. And then where we are. Yes. The reason we want to do that is because Marco and Tommaso showed if there is a graceful labeling of some zillion graph, by the way, we came up with the name zillion, but they showed the important result about it. Then there is a 2-starter, right, where we kind of, the path becomes 2m plus 3. It's doubled, and then a few points are added. And we double every cycle, right? Every cycle becomes 2 cycles of the same length. And moreover, if for some of the cycles, when we add some number, this epsilon is actually the number of edges in the zillion graph. If that different set within the cycle intersects the different set within the path, then we can actually do more. We can do this the same extended, we close up the path with an infinity point, and we double a bunch of paths. Sorry. And yes, we make the paths twice. And also we can double the length of paths. And let me maybe show a picture. It'll become a bit more obvious. Okay, so here's a zillion graph. Here's a graceful labeling of it. And what we're going to do is we're going to double this, like make this. Okay, there we go. We're going to double each point. Right. Then we're going to add 9 to every point on the bottom part. Now that doesn't change any of the differences, of course. And now what have we got? Well, actually, wait a minute. Yeah, one more step. So we're going to add an infinite point and join up the 1 and the 10. So we get that difference of the thing we added. What did we add? We added 9, which is 1 more than the differences we had. We had 0 to 8. Sorry, differences were 1 to 8. Labels were 0 to 8. Yeah, okay, so we've got the odd cycle there. There's our 2m plus 1. And we've doubled all the cycles, right? Where there was a cycle, now there are 2 cycles. Well, what we also want to do, so there's an overlap here. This one. Plus 5 is minus 4 mod 9. So there is actually an overlap here. All right. So we switch those 2 edges reduced. See that plus 5, we're going to put it across, and look at that. That's a plus or minus 4, and that's plus or minus 5. So we switched those 2, and now we have a cycle of twice the length. All right, so that's sort of the general idea of how this construction works. Okay, so what we were able to show was that the zillion graph in general has a graceful labeling whenever this bound is true. And I won't take you through the details of that bound, but the important thing is it's linear in the number of even cycles and exponential in the number of odd cycles. So every time I have an odd cycle, or the more odd cycles I have, the bigger my bound is going to be exponentially. But even cycles only add a linear factor. Okay. All right, so how do we do this? Well, the idea is to sort of splice together factorizations or graceful factorizations of graceful labelings of zillion graphs. So it's much easier when the graphs are even. So let's look at the even case first. The idea is we're going to take two copies of this thing. It could be any graph, any zillion graph, but I'm going to start with this as a sort of example. I'm going to join this to another graph, looks exactly the same, could be different, but it's going to look the same. And so the first thing I want to do is back up. I should point out what I'm actually using here is an alpha labeling, not a general graceful labeling. In an alpha labeling, you can divide the vertices into two parts, which I've done here, and all the edges go between the two parts. And further, the top part there, the small part, all the labels are small, less than a certain value, and the bottom part, the large part, all the labels are bigger than a certain value, and all the edges go between these two parts. Okay, and here's this gracefully labeled example. Okay, right. So the first thing I'm going to do is all the small ones, I'm going to subtract enough, and all the big ones, I'm going to add enough. And the idea here is to make room for this thing. Okay, right. Whoa, 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 I'm going the wrong way. There we go. Right. So I plump in my new value, my new graph here, and everything's looking good. I've got a new, bigger zillion graph, except the path isn't joined up. So I join it up. And what I've done here is I've really kept track of the endpoints of the paths. And I want to emphasize this is the hard part, and I'm really suppressing this, but I've made it so that the endpoints of the path are exactly the difference that I'm missing. So when I add that edge, boom, look at that. Now it's a zillion graph. I added one edge instead of having two paths of length 1. I now have a path of length 3. Okay. Oh, right. Now I just add to everything to get it to start at 0. So it's officially a graceful labeling. Okay. And now I can do that again, and it'll all work. And I've sort of made it again so that these endpoints of the path are nice in some sense. Okay, so how do I deal with the odd cycles? Well, it's really a similar idea, but I can't do alpha labelings, right? Because odd paths, you can't alpha label odd things. So we start with a zillion graph, which I'll call gamma. And in this example, it covers all the differences plus or minus 2 to 7. And I want to add an odd cycle to this graph. So I do that. And the way I do it is I add a path, which I've called C. I add a path, okay, and we know we can gracefully label a path. And then I add this point out here, which is exactly difference 8, which is the next difference. So it's the smallest thing I could have done, right? And I could make this path be as big as I want, right? Yeah. Okay. And then I pick up this difference 19, which is a bit annoying. So I'm going to have to sort of keep adding stuff to make this all work. And what I'm going to add is I'm just going to make the path longer. Okay, so here's some stuff I'm going to add. And what I want to do, remember, I want to control the endpoints. So let's say that I want the endpoints to be -6 and 13. So what I'll do is I add 2 paths in here. This covers 15 to 18 and 20 to 23 differences. And then that 19 I've just brought down so it doesn't get in the way of the picture. And then, but now I actually, again, I have 2 paths. So I need to join up these 2 paths and this one, by the way, was handily enough, 14. Okay. And I do that by adding a big long path, which I've called P1, and I haven't explicitly said what it looks like, but I can label P1 in such a way that it's got -22, which gives me difference 25 when I join it up with the 3. And where do we go? Here. 20, which gives me difference 24 when I join it up with the -4. And then I label this thing so that the endpoints of that path are -22 and 20. Okay. And then now I've got a new zillion graph. It's got a much bigger path. You see why we start getting exponentiation. But what I've done is I've added an odd cycle, and this is gracefully labeled. Okay. So what this lets us do is, because we have a graceful labeling, we have, where's it gone, a solution to OP sigma. And this is nice. This is the nice part about Marco's result, is that once we have this graceful labeling, we can use it to create a solution to the Oberwolfach problem, either when it's the regular Oberwolfach minus a 1 factor or plus a 1 factor. It gives us it all. Again, these bounds, linear in the number of even cycles and exponential in the number of odd cycles. Okay, I'll just mention that another way to go here is taking the lambda = 2 problem, and we get solutions to that as well. I won't go into that. I'll just finish up with a few conjectures. So we've talked about these zillion graphs and graceful labelings of these graphs. And one of the sort of interesting questions is, how big does your graph have to be gracefully labeled? And so we conjecture that there's actually a polynomial, f and x, y, and x and y here are going to be the number of cycles. Right, sorry, this is the first one. Where r is your maximum, the number of cycles of maximum length. If your path is big enough, then you can gracefully label. And what we're saying is big enough here is polynomial. That's the conjecture. We actually think that stronger results are true. So in particular, if there's a quadratic polynomial in with the number of cycles, right? So if the path length is quadratic in the number of cycles, then you can gracefully label conjecture. So this, furthermore, f is linear for bipartite zillion graphs. We actually proved that, right? The previous theorem, the one that actually shows that result. So it's so we know it's at least true for that. And another sort of reason we think this might be true is that Kotzig in 84, well, he didn't actually show this, but his proof is very easy to modify to show this, that if you've got some number omega odd cycles, then it must have at least omega plus 2, so quadratic in omega, in order to be graceful. Okay, so that sort of supports the conjecture. It says you can't do any better than quadratic. Like, it's not going to be any less than quadratic. And then the final conjecture is that basically it's quadratic in the number of odd cycles and linear in the number of even cycles. And thank you.